Hi everyone, this is Mr. Ruhoy, and this is an Algebra 2 video for solving exponential equations. In this video, I'm going to show you examples of 6 different types of equations, 2 of which can be solved without logarithms, and then the other 4 will need logarithms to be solved. And that's where you'll really see why logarithms are so important. They can allow you to solve for a variable that might be in your exponent, because you can't solve for a variable in an exponent using traditional methods. That's when logarithms become very useful. So the first 2 examples I have are solving exponential equations where the variable is in the exponent. And what we want to do is we want to set the exponents equal to each other and solve for x. That only works if the bases on the left and right side of the equation are the same. If the bases aren't the same, these are the steps that you need to follow, and that's what we're going to follow in this first example. So we have this equation 3 raised to the 2x minus 2 power, so that 2x minus 2 is the exponent. And then we have on the right side 81 to the first power. So those bases, the 3 and then the base 81, are not the same. So we need to find a common base. That's our step 1. So step 1, to find the common base would be 3. And in step 2, we can rewrite each side of these equations so that they have that common base, like this. On the left side, we're going to leave it as 3 raised to the 2x minus 2. But on the right side, we're going to rewrite 81 as 3 to the 4th power, because 3 to the 4th power is 81. Now they both have a common base of 3. And when they have a common base, our step 3 is to set the exponents equal to each other. So we can just take the exponents. We can ignore the bases for now and just set the exponents equal to each other, because our goal here is to solve for x, and that's our step 4. Now that the exponents are set equal, we can add 2 to both sides, divide by 2, and you solve for x, it's 3. So let's take a look at example number 2. So we have 2 raised to the 3x plus 3, and then we have on the right side of the equation 4 raised to the 4x minus 1. So right now the bases are not the same. We have a base of 2 and a base of 4, but we can find a common base of 2. And we can rewrite that 4 on the right side of the equation as 2 raised to the 2nd power. Now this question is different from the first one because on the right side of the equation, there was already this exponent with a variable. And I'm referring to the 4x minus 1. So what we need to do is we need to multiply those together. We can multiply the 2 in the new exponent, and we can multiply that by 4x minus 1. So that's our brand new exponent. And we're allowed to do that because of our properties with exponential terms. So now we have a common base of 2. We can set the exponents equal to each other. 3x plus 3 equals 2 times 4x minus 1. And now we just need to solve for x. We can distribute, we can combine like terms, and you can see that x is then equal to 1. I'm always a fan of checking your work after you finish a problem. You can take x equaling 1 and substitute that into the original equation, into each side, and you can evaluate it and make sure they work out the same. So let's get to our next examples. If the bases can't be rewritten, the first 2 questions we did, it was pretty easy to rewrite the bases. We just found a common base of 2 and 3. But if there's an example where there just isn't a common base, then we're going to have to use logarithms. So if we look at this first example, example 3. So we have 3 to the x power equals 20. So 3 and 20, there's no common base between those 2 numbers. So step 1 is to isolate the exponential term on one side of the equation if necessary. We don't need to for this one, but I'll show you an example later where we have to. Step 2, take the log of each side. The base of the logarithm should be the same as the base of the exponential term in the original equation. So the base in this question that we're looking at is 3. That's the base. So what we're going to do is take log base 3 of both sides. And that's what it looks like right here. log base 3 of the entire left side of the equation, 3 to the x. And that's going to equal log base 3 of the entire right side of the equation, which is 20. So it's really just taking both sides of the equations and placing that inside the parentheses for our logs. And it's so important that the log, the base of that log, is the same base of the original exponential term. Now, it doesn't have to be, but if you do that, something really nice will happen. Because our step 3 is now to solve the resulting equation, and this is how you do that. We can apply our logarithmic properties, the power rule for logs. That says that if there's an exponent, I'll circle that here, if there's an exponent, we can take that and we can move it in front and multiply that to the log. So now we have x times log base 3 of 3 equaling log base 3 of 20. Now this part's really good. Log base 3 of 3 is equal to 1. If you were to type that in your calculator, you would realize that, and it makes sense because if we were to rewrite this in exponential form, you'd circle the base, run the race, and set that equal to 3. So that makes sense as well. But my point is, log base 3 of 3, if what you're taking the log of and the base are the same, that's equal to 1, which means we can just cross this out, replace it with a 1, and now all we're left with is x on the left side of the equation. And you solve for x. And then that's equal to log base 3 of 20. Log base 3 of 20, that's approximately 2.73, but I really prefer it when we just leave it as our log, leave that as our final answer. I just want to mention that it's 2.73, just to make you realize that log base 3 of 20 is a number. It's a number, it has some value. But it's very common for a question to ask for the exact value, so that's when you're just going to leave it as the logarithm. And that's it. That's how you solve for x. I got some more examples of that. Here's example number 4. So we got 3 equals e to the x minus 4 power. So the base in this equation is e. So we're going to take the log base e of both sides of the equation. Now log base e is actually our natural log, so we can just write the ln, the natural log, of both sides. So we have the natural log of 3 equal to the natural log of e raised to the x minus 4 power. Our properties for logarithms allow us to take this exponent and multiply it in front. So that's what I did in the next step. We have natural log of 3 of x of 3 equal to x minus 4 times the natural log of e. Now, natural log of e, that's equal to 1. So what we can do is we can cross this out and replace it with a 1. Which means our equation is now very simply the natural log of 3 equals just x minus 4. And now we just need to solve for x, and x is equal to the natural log of 3 plus 4. And that's how I'm going to leave my final answer. You could type that in your calculator, natural log of 3 plus 4 equal to x, but that's our exact value. It's not rounded, and we're done. Here's another example, example 5. This one has a little bit more to it, just some initial work we have to do. If you recall, step 1 for solving these equations is to isolate the exponential term if necessary. So that's what we should do first. We should get the 2 raised to 2x plus 1 by itself first. So we should get this by itself. We need to isolate that. And the way you would do that is to add 2 to both sides. That would give you 4 times our exponential term equals 13, and then you want to divide both sides by 4. So that's what we're looking at. Now 13 divided by 4 is 3.25, but I'm just going to leave it as a fraction. I typically don't like decimals, so we'll leave it like that for now. But now we're going to continue with our methods. We're going to take the log of both sides, and the base we're going to use for that logarithm is the same base we have in this exponential term, base 2. So we're going to take log base 2 of the entire left side of the equation, and then we're going to set that equal to the log base 2 of 13 over 4. We're taking the log of both sides, taking both the left and right sides of the equation and just placing that inside our logarithm, which we chose to be log base 2. So our properties say that we can take this exponent and place it in front. So we're going to multiply that to our logarithm. We have 2x plus 1 times log base 2 of 2. That's equal to log of 2, log base 2 of 13 over 4, excuse me. And then log base 2 of 2 is just 1. So then our equation is then going to be 2x plus 1 equal to our logarithm. And the goal of this whole thing is to solve for x, so we're going to subtract 1 from both sides, divide the entire right side of the equation by 2, and that's how you get the logarithm. That's how you get x by itself. All right, so I have one more example. And this is a word problem that my students might recognize from us doing before. And at the time, we didn't know, we hadn't studied logarithms yet. So the way I said you can solve for your exponent, solve for your variable, excuse me, which was in the exponent, is to solve for graphically, which you can always do. You can always solve an equation graphically. You can always check your answers graphically. But now we know what logarithms are, so I wanted to go back to this question and show them how to do it. In 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. So write an exponential growth model giving the population y in billions of people, and using t to represent time, which is in terms of years, and that's after the year 2000. And then let's estimate the year when the world population was 7 billion. So if we want to write a model for this, we're going to use our standard growth model, which is using A to represent the initial amount, in this case, the initial amount of people in terms of billions of years. R represents the rate of growth, and then I just want to point out 1 plus R is our growth factor, and then R is just the growth rate. And then T is our time. That's, in this question, that's going to be in terms of years. So we're going to use 6.09 to represent the initial amount. The rate is going to be, the value of R is going to be 0.0118, because in the problem it was given to us as a percentage, but that needs to be converted into a decimal. So you have to move the decimal point over 2 places. So finally, here is our growth model for this question. And then we want to estimate the year when the world population was 7 billion. So we're going to set that equation equal to 7. And now we need to solve for our variable, which is in the exponent. So for this question, we can solve for that using logarithms. Now, there are actually 2 kind of ways you can approach the logarithms with this. I'll show you one method which follows exactly what I did in the previous examples. And then I'll show you a kind of a different way, which is also correct and might be a little bit easier. But, you know, it's up to you which way you prefer. The second one I would say is more common, truthfully. Anyway, step 1 is to solve the exponential term to isolate it, to get it by itself first. So let's divide both sides by 6.09. Now, we want to take the log of both sides. The base in the exponential term is 1.0118. So that's the base we're going to use for these logarithms. Now, looking at it, it looks kind of messy. That's why the alternative method I'll show you in a moment might be a little bit more appealing. But this follows exactly what we did in the previous questions. Also, I decided to leave the 7 divided by 6.09 as a fraction because it's a messy decimal. And typically, you don't want to round along the way with your question. You only want to round at the end. So I'm leaving it as this. So what I did was I can take this exponent, using our logarithmic properties, we can move it in front, multiply it. And the log of that base, which matches the number in the parentheses, just becomes 1. So then on the right side of the equation, all we're left with is just t. And that's our answer. And if we approximated it, if we typed it in our calculator, figured out what the log of 1.0118 of 7 over 6.09, it works out to be about 11. Almost 12, but because because it is less than 12, that means that in the 11th year, the population will reach 7 billion. It's just going to be towards the end of the year, but in the year 2011, the population will reach that 7 billion mark. And that's how you solve an equation where the variable is in the exponent. Now, here's the alternative method that I mentioned a couple times. Alternatively, this might be a little bit easier, but this is where we were in the question, where we wanted to take the log of both sides. Now, in all these questions, I told you to take the log base, use the base for your logarithm to match the base of the exponential term. So I said use log base 1.0118, but it was kind of messy. Truthfully, what you can really do is you can take the log of any base of both sides. So what I did here is I just took the log, which is base 10. I just took log of both sides. And then I continued the problem. I'm able to move the t in front and multiply it. And then you can just divide both sides by these logarithms. And what you can do is you can type that in your calculator. In your calculator, you have the log button, log base 10, and you can divide those, and you're going to get the same exact answer. The reason this works is because this right here is exactly the same as this statement here. And those are identical because of our change of base formula. Change of base formula says you can take this term right here and you can separate it using log base 10, using division. And that works. That gets you the same exact answer. So what I just want to share with you is that sometimes when you're doing a logarithm, solving an exponential equation using logarithms, and you have really messy numbers, and in the end you just want to get a single answer, a single value as your answer, sometimes maybe you just want to take the log base 10 of both sides. It might make it a little bit easier for your calculator work. All right, that's about it. Thanks for watching.